In this video, I'm going to introduce the concept of concavity and talk about the second derivative and its relation to the shape of functions. Take a moment to pause the video and read and try and answer the question given here. Now that you've had a chance to try and calculate these slopes for yourself, I would estimate the first slope is approximately -1, and then that changes to a slope that is maybe somewhere around 1/4, and finally a slope of something that maybe is approximately 1. What can we say, or what do we notice about dy over dx in this graph? Well, in this case, I notice that dy over dx is increasing as we go from left to right on the graph. Now, this is in contrast to the second graph, where we start with a slope that is approximately 1, transition to a slope that is approximately maybe 1/4, and a third slope that looks a little not quite as steep as -1. We'll say -1/2. In this second graph, we would say that dy over dx is decreasing. The slopes are getting smaller in value as we move from left to right. Well, there is a word that relates to these two general shapes of graphs, and that word is concavity. In the first graph, we would describe this graph as being concave up. A graph where the slopes are increasing as you go left to right, and you'll notice the shape looks kind of like what you get from a upward-facing parabola. Whereas in the second graph, we are going to call this concave down. And again, the general shape of a downward-facing parabola, approximately. But let's analyze this idea just a little bit more using what we know about derivatives and our notation for derivatives. When we say that dy over dx is increasing, what we are saying is that the rate that dy over dx changes is positive. And keep in mind that whenever we use the phrase dy over dx, we mean the slope. So in this first graph, the slopes are changing at a positive rate because they are increasing over time. Well, this phrase, the rate that something changes, is just language for the derivative of something. So what we mean here is that the derivative of the slopes is positive, greater than 0. Now, this calculation here, the derivative of the derivative, is referred to as the second derivative. And the second derivative tells us about the rate that our slopes are changing. And in this particular case, we're just looking at an example where these slopes are changing at a positive rate. They are getting larger and larger numerically. In the second graph, instead, we see that the slopes are decreasing. And so we would say, when we take the derivative of those slopes, we are getting something that is less than 0, or we have a negative rate of change because those slopes are changing negatively. It might be nice to develop some notation for this thing that we're now calling the second derivative. So if I want the derivative of the derivative, one way that I can write that is I can say d squared y over dx squared. This thing means the second derivative of something. If we wanted to use our y prime or f prime of x notation, well, y prime is the first derivative, so y double prime is the second derivative. Or using function notation, f double prime of x means the second derivative. And we are just now kind of seeing this relationship between the second derivative and what a graph looks like. And we are noticing that if the second derivative is positive, that we get this concave up shape. And if the second derivative is negative, we get this concave down shape. Let's take a look at an example problem. The graph of h of x is given here. You're going to use this graph to try and estimate answers to the following. Pause the video and see if you can come up with some responses to each of these questions. Now that you've had a chance to answer these on your own, let's take a look at these three problems. Over what interval is the graph concave down? Well, concave down means that the slopes are decreasing in value over time, and we get this part of the graph that looks like it's a downward facing parabola. And I don't know exactly where it stops being concave down, but it seems to be somewhere around x equals 1. At that point, it switches to being a graph where these slopes are increasing as we move towards the right, or being concave up. So let's write out some intervals for each of these. And again, I don't know exactly where it switches, but it appears to be from negative infinity to somewhere around x equals 1 for our concave up, and for our concave down starting at 1 and continuing to infinity. We're assuming here that we have a cubic graph and that the graph doesn't turn around again at some other point that we don't see off the graph. Well, what can be said about dy over dx on this interval? Well, in the blue part of the graph, the concave down part, we know that dy over dx is decreasing. And if that is decreasing, we mean that the rate that these slopes are changing is negative. And a way for us to write that is to say that the second derivative of the graph in this case is less than 0. As opposed to the red section of the graph where these slopes are increasing as we move to the right. And we would say that d squared y over dx squared is greater than 0, or the second derivative is greater than 0. The last question asks at what point the graph switches from being concave down to concave up. And we decided that that point was approximately when x is equal to 1, maybe around 1 comma negative 3. Okay. Now this point we have a slope that is neither increasing nor decreasing. If that is true, that means that the rate of change of the slope, dy over dx, must be equal to 0. Well, this point, you may remember, has a name. When we studied cubic equations in AAT, or in Algebra 2, we learned to call this point the inflection point. And what is unique about the inflection point is that the second derivative is equal to 0 at that point. The slope is neither increasing nor decreasing. At that moment, there's just a brief moment where it is neither concave up nor concave down. Well, let's just put together a little bit of what we have learned here about the second derivative. The second derivative tells us how quickly the slopes are changing and whether they are changing positively or negatively. And we learned that if the second derivative is greater than 0, we have a shape that is moving in a concave up, what we're going to describe as concave up. And that if the second derivative is less than 0, we have something that is concave down. And then we've seen one instance of an inflection point, and we have decided that the second derivative at that inflection point is 0. But what made it an inflection point was that we also saw that the second derivative switched signs. And what made it an inflection point was not only that the rate of change of the slopes was 0 at that point, but that it switched from being concave down to concave up.